Hello, and welcome to Technically Speaking, where scientists and engineers come together to chat about a common interest, share knowledge, and satisfy some curiosity. I'm Antonia, and I'm joined by Laura and Emma to talk about nanoparticles and what they're used for. So, Laura, you brought this topic up. How come?
When I was still in academia, quite a few years ago now, and I was doing a lot of work on radiation science and material science as well. Lots of scientists seem to be working on nanomaterials for different applications like radiation sensitization and electronics. And it seemed kind of novel and new. It actually turns out it's not. Yeah, it's not the newest technology I thought it was, but it's new to me, which was exciting.
Yeah, and sensitization, we'll have to discuss that later. And I actually did an internship where I was working with nanoparticles. I was helping make them with better quality. I'm not sure I actually know how they actually work. I know what I was doing in that small context. I'm hoping, Emma, with your background in physics, you might be able to explain how they work.
Yes. I think I'm completely the opposite to you as well, whereas I know how they work, but in terms of real-life applications and why is this important, I do not really know. So yeah, I hopefully can definitely share some stuff on the quantum side of things, which is very kind of scary word sometimes. But in fact, it's very much my bread and butter.
I'm glad someone is comfortable swimming in that uncertainty. Laura, when you were learning about nanoparticles in your field, what were the key things about it?
Well, from what I can tell, the reason nanoparticles are so interesting is because they're small enough that they have different properties than standard size particles. So a nanoparticle is defined as something that's less than 100 nanometers in diameter generally, which is about the same size as a virus particle. And Emma mentioned something about quantum effects, and essentially it means they're so small that the electrons kind of act differently. They're not averaging out all their behavior, and they end up occupying sort of these discrete energy levels that you hear about when you are looking at individual atoms. That's what I understand about it anyway, but I'm hoping that Emma can provide a slightly more thorough explanation.
Yes, hopefully. One thing to understand, I think, about when things behave as quantum particles versus classical particles, where classically particles might follow Newton's laws. Particles follow quantum regimes when they are one of two things, or both, I think, actually. So one of them is really, really cold temperatures, where the behavior of the particle seems to change from regular temperatures, like literally around 0 Kelvin, or when you're at really, really small scales and really, really small sizes, they start to exhibit these quantum effects. The quantum size effect means that I feel like I'm repeating exactly what you said, Laura, you just explained it amazingly.
Nice.
But when you have these small scales, the individual atom becomes, in terms of size fraction of the scale you're looking at, it becomes almost all of the scale you're looking at, if that makes sense. Whereas if you're looking at larger scales, the individual atoms are so small compared to that, you look at this kind of larger behavior. Whereas on the smaller scale, you can it doesn't necessarily work like this, but imagine if you're looking at the right scale, you can actually see the atoms and see how they behave more exactly. And how they behave is quantum mechanically, which basically just means strangely and weirdly.
So almost like if we imagined these particles were individuals instead, or the atoms are individuals, or you're looking at an entire crowd. Like, people could be wiggling around weirdly, but generally they're all moving towards in one direction.
I would say that's a really good analogy. Or even just like a loud conversation in a room. When you're at these kind of quantum effects, you can start to hear specific things that people are saying, and you get to resolve individual behavior of the individual atoms rather than this kind of mass property.
So, Laura, you mentioned that nanoparticles tend to be below 100 nanometers, and Emma, you've said we're looking at sort of more onto the scale of individual atoms instead of a collective mass of a material. How many atoms are we talking about?
From my maths, which isn't hugely accurate, it was a rough back-of-the-envelope calculation, as we like to say. It's about 200 to 1,000 atoms. Obviously, that depends on the size of the nanoparticle and what it's made of. But that is quite a small number. If you look at things that I was modelling, which were some fairly longish polymers, there were thousands and thousands and thousands of atoms in my atomistic modelling simulation that I was working on. So these are really small.
I mean, also to add context, like a mole of a substance is 10 to the 23 atoms, which is lots and lots.
Yeah, and if we had, like, was it a mole of, say, carbon dioxide, it's 44 grams.
I can't really visualise what a gas looks like as 44 grams, though. I guess you're choosing that, Antonia, because you tend to look at carbon dioxide a lot in your job in sustainability and energy research.
Oh, but I don't know if that's actually a mole. Now I've questioned myself. I was slightly wrong. It's like 43 grams.
Close enough.
Oh, wow, that's so close. So I've just talked a lot about physics and quantum mechanics, but as I said, I don't really know applications and things. So where are these nanoparticles? Like, what are they used in, and what are they made of, even? Can they be made of anything?
The one that I've heard most application of were nano silver and gold, and they exhibited properties we didn't necessarily see in their normal size versions. It's weird. I'm like thinking of the mini version versus the big version. It's very different.
Yeah, I suppose gold's quite a well-known one because the nanoparticles are often red rather than golden in colour. That's because they've got different optical properties because of their size, and that one of the reasons they're really famous is because they were used to colour glass way back when. So it's a very good example of glass from Roman times. And it's a cup, and it's green if light is passing through it, as being scattered around it, I should say. So if you're just looking at it under normal daylight, if you put a light inside of this glass vessel, it suddenly turns red. Difference between transmission and reflectance.
I just googled that. That's amazing.
That's pretty cool.
Yeah, so it's quite a good visual example of the difference between nanoparticles and a normal size material, if you like, Antonia.
Yeah. That also says to me, yeah, nanoparticles, whilst seemingly a new technology, we've actually managed to, as a society, work with nanoparticles.
I think the reason nanoparticle technology in science has become so much more active as an area of research recently is because technology developed that we could actually see them. You know, we had microscopes. It was the 1980s when some crystallites of a size range in nanometers were seen to have different properties, and they did so much research into them to figure out why. It kind of set off this whole new research paradigm, I guess.
Yeah.
Antonia, you mentioned silver as well. That tends to be used as an antibiotic, doesn't it?
Yeah, so they found that there's antibacterial properties with nanosilver. So you have nanosilver plasters, other types of wound dressing. I wanted to find out how it works. And apparently there isn't a consensus on the actual mechanism that is happening between the silver particles or silver atoms and the bacteria that it is basically killing. Researchers have a number of suggested mechanisms, which I thought was interesting, that it's still quite a new field.
Yeah, I think you might have read the same research article I did. It was in the Journal of Nanomedicine. I think it's published in 2020. It's about dentistry, its applications there, wasn't it?
Yeah, they had a great infographic, I suppose, of different possible interactions between silver and a bacterium.
Yeah, I'm going to guess that one of the reasons it's so popular is because the particle size is small enough that it can penetrate the bacterium and do various things to it. Specifically, why silver and not some other nanoparticle? I guess it's because the exact properties that it has. Did that infographic tell you? I don't have it in front of me to refer back to.
No, they said mostly that, again, it was crossing the membrane and essentially denaturing enzymes or even the protein or DNA. But why silver? Not sure about that. Something about the silver plus ion.
I can say from a kind of protein science perspective, like the proteins are held together by bonds and the ions that are very, very important. So I can definitely imagine that any kind of shift in charges that are around the proteins can completely change the structure of them, which is like deadly to things like bacteria if it can actually get inside and affect it.
I wonder if one of the reasons it's so difficult to figure out is because even in a bacterium, there's an awful lot of chemistry going on in there, and it's really difficult to unpick different biochemical mechanisms. So it's probably doing multiple things, and it's having these multiple effects, which seems to be similar to what happens in radiation sensitization, which gold is quite a common nanoparticle to use there as well.
Yeah, so what happens in that case?
Ooh, so I read so many journal articles about this and had so many facts spinning through my mind. There are loads of different ways that gold nanoparticles can be used as a radiation sensitizer, which essentially means it makes certain cells more sensitive to radiation. So the idea is that you can create the gold nanoparticles to specifically target tumour cells. And then when you undergo radiation therapy in a hospital, the tumour cell is more likely to be affected by the radiation than the healthy cells.
Oh, wow.
Yeah, so some of the mechanisms involve radiation chemistry, which I have a little bit of a background in. So when the gold nanoparticles absorb the radiation, they can then undergo all these different electronic effects that then creates lots of free radicals, which, as a lot of people know, tend to do damage to biological structures, including DNA. From a physicsy point of view, Emma, I know we get taught this in school, so hopefully you can help me refresh my memory of this. You get phenomena like Compton scattering and the photoelectric effect.
Oh, yeah, classic.
Yeah, and gold's really good at absorbing radiation because it's quite a heavy element and is fairly biologically inert. So it's fine to put it in your body, send it to the tumours, and then have all these physical phenomena happening to it that then cause chemical effects.
Oh, nice. Yeah, no, I had a bit of a flashback when you said Compton scattering then.
So what is happening with quantum scattering? Because I don't know what that is.
Compton. Not even quantum. Compton. Compton is just was a physicist, and it is essentially conservation of momentum between photons and particles interacting, and it's just a way that they can interact with radiation. It's like used a lot in particle physics, but it's really interesting to see it and explain this kind of medical biophysics background, which I've not seen it in that context before.
So if we're staying in the biological realm, another application of nanoparticles was using zinc oxide and titanium dioxide in sunscreen. Why is it beneficial in sunscreen?
Nanoparticles, essentially because you can apply them so thinly that they don't make you look like you just coated yourself in white paint.
Oh, interesting.
So it's more for aesthetics. You could apply non-nanoparticle zinc or titanium dioxide, and it would still have the same effect of protecting you from sunlight. And the way it does this is to absorb and then reflect it back out.
Absorb the UV.
Yeah, so the UV doesn't reach your skin, it's just reflected back out by the zinc oxide or the titanium dioxide, which sounds kind of boring.
I mean, if it works.
Yeah, there was a little bit of a controversy that kicked up, about 10, 15 years ago, I think, maybe even longer. There was some suggestion that zinc oxide in particular could actually help cause cancer rather than help prevent it.
Oh no. Did we find out whether that's the truth or misunderstood science in the media?
I think the consensus is that in the laboratory study that kicked off this idea, yeah, it did seem to have adverse biological effects. But one of the studies involved like using lung cells, and obviously you're not likely to expose your lung cells to sunlight. Your body is covered in a layer of dead skin cells, and not a lot penetrates that. So even if the zinc oxide was producing all these radicals similar to how the gold does in cancer therapy, when it's inside the tumour, the zinc oxide might be doing the same, but it's not penetrating your skin. Whether it's producing these radicals, I'm not 100% sure actually. It could do, I guess, if there are other things in contact with it, because one of the advantages of nanoparticles is they've got this really big surface area, right? So that can produce lots of chemical reactions potentially. But no, it seems like best advice is still to wear sunscreen.
And wear my sun cream every day, just in case. Even though in Edinburgh there's not that much sun.
But even with cloud, there is some solar radiation.
That is true. UV can still be quite high when it's cloudy, can't it? And one of the things the manufacturers did, just in case there was an effect that they weren't aware of, was to kind of coat the nanoparticles in something that would help prevent any radical production. So there you go, they doubled down.
That's good. Because I did have a concern about if silver was really good at killing bacteria, what would happen to humans then? And apparently that is not a concern because it's, again, on the surface. Yeah, our skin is actually a really good barrier against foreign things.
Yeah, I guess beyond what we've mentioned, so silver and gold and the zinc oxide and titanium dioxide, when it comes to radiation therapy, there are loads of different nanoparticles that you could use. And the exact one that you would use depends on, I think, the type of cancer and the organ that it's affecting. We could do many, many episodes on just radiation sensitizers, I think.
Wow.
Maybe we should move on. We can maybe revisit it at some point.
But we've managed to sort of like fine tune. If you were going for a lung cancer, we'll use these types. If we're going for pancreatic, we might use something else.
That's what I understand of the research, yeah. It sounds like it's like a vast field. So it's like just one application of nanotechnology, right? Sounds like there are lots of others.
Yeah. So when I was doing my internship, the company I was working for, their product was a quantum dot, which is a subcategory of nanoparticles. They were looking at applications in TV and lighting, as well as potentially medical diagnosis and screening. It kind of reached, you might say, a wide spectrum.
Is that a quantum dot joke?
Yes, of applications.
You might want to explain that one.
My best understanding of quantum dots, they exhibit semiconductor properties. When they absorb energy, they then emit it, in my case, as light, or maybe they could emit it in other lengths of the electromagnetic spectrum, and therefore you could get something useful out of them.
Yeah, I was actually reading a bit about it, and people were comparing quantum dots in television to LEDs. So LEDs stand for light emitting diode, and so they're both kind of electronic components. But a quantum dot has very specific tunable optical properties, so you can make a quantum dot to kind of emit whatever light color you want, and that's why, and people were saying that you get much more vibrant, crisp colors in TV when you use quantum dots compared to LEDs, because they're just much more efficient, and you can actually tune the property of light that you want it to emit a lot more accurately.
Yeah, so you could basically almost like narrow down what wavelengths you were going to emit based on the size of the particle that you've produced.
I think Emma and I both use the term optical properties and not really defined it. It's how it interacts with light, isn't it? That's what I take it to mean, yeah.
I just took it as light-related.
It just gives you the idea it's turning it into some sort of tiny, tiny little lens. It's not quite what it does. There's also the idea they can be really stable, isn't there? So there are like lots of properties of nanoparticles that give them really specific advantages, which is why they're researched so much for very specific applications, it sounds like.
It sounds like they're a bit kind of, the world is your oyster. If you can make something small enough as very repeatable and very producible, then you can kind of have a goal in mind and try and make something that can achieve that, because optical properties of things, so how much light they reflect or anything else, even in some cases how much light they bend, is a very desirable quality to have depending on what you're looking for. So I think that's why people get so excited about nanoparticles, because it's kind of like, I'm not going to say the stem cell of, I don't know, chemistry, but it can kind of be whatever you want it to be, as long as you tune it in a certain way, I think, is how I'm seeing all of the buzzwords around nanoparticles kind of make sense to me, and all the different applications as well.
I think that's a good place to end the conversation. We were learning about, I was learning about what is the quantum size effect and how that related to work that I did almost 10 years ago in a little lab making quantum dots. We learned about the definition of a nanoparticle and their uses, particularly in medicine, and the future is bright with quantum dots. I think I've saw that from a TV advert. But also, but we know that they work, and we could make them do all sorts of things with electromagnetic radiation.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.